which is artificial neuron, which was not adaptable. We are trying to bring some adaptability into the artificial neuron with the same philosophy that, okay, if it gets more than a desired amount of input, it's going to trigger an output. And the way we trigger an output is via this thresholding function, a step function, which basically tells, okay, if this W transpose X is greater than 0, that is what we mean by sufficient, it's going to give you a 1. If it is less than 0, if it's negative, then it's going to give you a 0, right? So that is the perceptron. Now, we can build a single layer of TLUs by stacking many TLUs one next to each other. Each TLU has a weighted combination. What is changing from one TLU to the other? The weights are changing, right? So every arrow has a weight. The weights need not be the same for all the arrows. So we take a linear combination and an offset. Okay, that is the bias neuron. Bias neuron, bias itself is not known, but the output of this bias neuron is always 1. So that means that it is B times 1, right? So again, specifically, suppose we are looking at the TLU number 1. The TLU number 1, what it basically gets is X transpose W1. So these are the sets of weights associated to the TLU1, and it sees an offset with a B1. Okay. So now the output of this TLU is TLU applied on Z. That is the output, right? So, and Y1 is TLU of Z1. Similarly, the second neuron basically gets X transpose W2. What is constant here between TLU1 and TLU2? The X is the same. So the same example is being multiplied with different combining coefficients. Okay. And you get a different bias, B2. The output of the second TLU is TLU applied on Z2. Okay, is that clear? So now each, you get an affine combination. So you linearly transform plus add a bias. You do this for the example that is there. What is changing from one TLU to the other? The weights and the biases are changing. Okay. So now let's go back to this more general case where we have n examples. Each example has p features. Okay, so let's let's recall the data that we have is x, which is n times p, n examples times p features, which is collected in x1 transpose all the way up to xn transpose. Each of this vector contains p entries. This is example 1 all the way up to example n. Okay. So now what is going on is the following. So I take, let's assume that we have two TLUs that require two outputs. So what you basically do is x1 with w1, which is the weights of the first output. This is weights of the second output. And you have b vector, which is b1 and b2. These are the weights. So now what you're basically getting is the TLU of this. So you're going to get Y1 and Y2. Okay, so you're going to get two outputs. Okay, so now this is for one example. Okay, so now I can compactly write this as TLU of X1 transpose W, which is the weights corresponding to all the arrows that you're seeing plus this bias vector. This is going to give you the two outputs for example one. So this is example one, first output, example two, or example one, second output. Okay. So you have for one example, I get two outputs. Now, I have n such examples, right? So n such examples. Now the overall output for n examples, you will basically get, this is output one, this is output two. Now, if I have n examples, I would get y11 all the way up to y1n. First output for all the examples. This is second output of all the examples. Here, what is changing is you apply TLU of X1 transpose all the way up to Xn transpose, multiply with W and B. Okay. So now what is important to notice at this point is all the examples. Examples are basically different flowers. To keep that running example in mind, each instance is one flower. I have n such flowers in my training data. Each of these instances, each of these examples have P features. P features sitting as columns of this matrix X. So I have feature 1 all the way up to feature P. Okay. Now, for all the examples, I'm combining with the same weights and adding a bias. Okay. So I'm not changing the weights and biases for different examples. The W's remain the same. So for the first example, I use the same W. For the second example, I use the same W. For the third example, I'm using the same W. Okay, so W is not changing with respect to N. The size of the W here is of the size P, which is a number of features, times the number of outputs that we desire. If we want two outputs, then W will be of size P times 2. If I have one output, that means it is one TLU unit. I have one output, it will be P times 1. What is crucial is W is the same for all the examples. Okay. So this is very important to keep in mind. You're not changing W for every example. I'm combining all the features from each example using the same set of weights. Now our goal is to figure out what this W and what this bias is. Okay. What is bias doing? I will tell with a picture in a few minutes. But what we are trying to do is we are trying to take a linear combination of our data with a W and B that we have to figure out what that is. We don't know what that is. I have to figure that out. Okay, I'll show how to do that for a simple case, which we will develop further as we progress. Okay, so what we now have is a single layer of TLU, which can have multiple outputs. X is our data matrix. W is the set of weights, which is called as the trainable parameters. We don't know what that is. We have to figure out what this W is. The bias is basically giving us an offset. This is also not known to us. We have to figure out what this W and what this B is. The activation function, which is a step function for the threshold logic unit. Okay. So the output layer compactly can be written as a linear combination of the features, the input matrix, the feature matrix with W and biases. Okay. So each neuron or each TLU unit would get a different bias. As we can see here, the one that I'm highlighting. So you would get as many bias variables as the number of TLU units. So for this particular illustration that we have, W would be of size. We have two inputs, which is two features, times three outputs. P times number of outputs. W is 2 times 3. Bias, I have three outputs. So I have three bias variables, B1, B2, B3. Okay, so those are the arrows that is going from a biased neuron to an input. I hope this is clear now. So how many arrows do I have in total? I have 6 plus 3, 9 arrows going from the input layer to the output layer. All these arrows, weights of the arrows are not known. Okay. What is deterministic here? The activation function or the step function, it basically is a computation. Whether Z is below 0 or above 0. It's going to do a deterministic thresholding operation. Okay. So now let's, given this context, we know what W is, what is B. That is what we have for our setup here for this example. Now, for a given task, how would you basically learn this, right? So let's do that with a simple illustration for a simple problem that we are going to generalize. And in practice, you will not do this exercise for every neural network task. We will see why that is so as it will become clear. So the input for us is the feature matrix X and the label vector Y. I have n examples, I have n labels, right? So it could be a regression task or a classification task, but we have the outputs. Now, this is n times P. This will be n times 1. Okay, so that will be the label matrix. Now, our hypothesis is for TLU, I'm simply using this phi function is the following. Okay. So even for regression, note that I'm using a non-linearity, right? So regression, I might require multiple outputs. I'm using X times W plus B, apply a non-linearity. Okay, that is my hypothesis or the prediction for my label. Okay. So far, we are very similar to the linear regression or the logistic regression depending upon the task at hand. Okay. Now, once you have figured out what these W's and B's are, what we get is basically a new point, that is the test point. The test point, you would get, say, X star. Okay, that is the feature of the test point. Our goal is to figure out what is the label, right? So it could be a regression or a classification task. And what you would do as a prediction is, I have figured out what the W and B is. You would do X star transpose W plus B. Okay, so that is going to give you the prediction of the label. Okay, so now this is how any ML model would work, right? So you figure out, I'll illustrate what one would do. And then once you have that, you get a test sample, you get X star, you linearly combine with the W's and B's that we have computed, and then you give a prediction. Okay. Now the question is, how would you learn this, right? So how would we figure this out? Now, let's take a look at one particular output. Okay. Say the jth output. our jth output is Wj hat. And for now, let's assume that we don't have non-linearity, right? So it's basically a linear combination and the bias is also zero. So I have J1, W1, X, J2, Wj2. So you're taking a linear combination of XJP, WJP. I'm looking at the jth output, right? So we have some linear combination. And now I have to figure out what this Wj vector is, which collects all this Wj1, Wj2, and so on, right? So now this loss function, which we'll set up, will be a function of this Wj, which is simply a loss between the label Yj and my prediction. Okay, I'm super simplifying it. I'm assuming that phi is, say, the TLU, I'm ignoring it. It's simply giving us a linear output. Phi is basically an identity operator for this discussion, right? To set up how one could potentially learn. And if our task is, for example, a regression task, what you would do is you would basically set up a mean squared error loss, which is Yj minus Xj transpose Wj square, right? So this is simply linear regression so far. How you would figure out? You would compute the gradient of this loss function with respect to the unknown parameter, set this to 0. By computing this gradient, what you would get is Yj minus Xj transpose Wj. So you have a quadratic, right? And then you take 2 times that, and with a minus Xj is equal to 0, you solve this linear equation. The way you would update this is as follows. So for each of the variable, you get the next iterate. I'm quickly recapping what you might have already seen. I'll write this and then explain. Some step size. Okay. So what you would do the same thing if you have biases. So you would have a derivative with respect to Bj and set that to 0. You would get some equation. You would solve this. So super simplification of our model. And what we have basically done is gradient descent update for what would look like a linear regression. Okay. So of course, we don't have this for our perceptron. Things will become more complicated. The point of this derivation that I did here is to emphasize that you will not be able to do this in practice, whatever we did for linear regression. The reason will become apparent as we further proceed with the discussion today. But what you need to keep in mind for now is the following. We now have a way to hypothesize a class label or a regression output as a linear combination plus some bias, which is known as affine combination, plus some nonlinearity. This is our hypothesis for our label. W and B are not known. W and B, they are same for all the examples. Now, if I look at one particular example and see one of the outputs, what we basically get is a function. I can set up a function where I would say that the hypothesis Yj hat should be close to the true label for the training data. I need this true for all the samples in the training data. Since all the samples are using the same W, I get a loss function, which is a function of W. A way to minimize that is basically seeing where the gradient vanishes I get a stationary point, and you work that out. What we get is basically this update equation. You start with some initial point. Every time I'm going in a direction, that would basically work towards the stationary point. That is where the gradient vanishes. And in simple words, you start with an initialization, you update that iterate for each of these weights by making the loss function smaller and smaller. So you have an estimate of the error. You want that to be small, right? So whenever yj is close to yj hat or yj is equal to yj hat, then this particular term would be 0. You don't update anymore. You kind of reach an equilibrium state. You're not updating anymore. Okay. So you start with the current iterate. You go in the direction of the negative gradient that is going to minimize that function, minimize the loss function, and eventually you update. So this entire thing is called as gradient descent. You might have seen this already in the previous module. But now what we need to keep in mind is I safely ignored what this phi is for the sake of this development. I also ignored that whatever task I have, I can basically solve that using a single layer of TLU. Now, does this work in practice? When does it fail? This is what we would like to understand next. So basically, for now, we have a single layer of TLU, which gives us multiple outputs. What is not known is the weights and biases. Okay. Now, let's take an example and see how to put this in practice. You can simply call this sklearn library to implement a perceptron. So again, let's go back to this running example where we have 3 classes. The data set itself has 3 classes of flowers. Now, for our sake of understanding, we'll look at a TLU with a single output, which does a binary classification. What that basically means is I'm going to classify this as either Iris setosa, or if it is not Iris setosa, it could be belonging to the remaining 2 classes. I will not further look at that fine grain classification, but I would just do Iris setosa or not. Okay. So now what are you doing? You have a single output TLU. It's a binary classification. We would have to learn the weights and biases. You could simply do this, whatever story I mentioned with the gradient descent, by simply calling this function, which is a perceptron. It takes data, which is X and Y as input. It is going to give you a class prediction. Okay. And also it's going to give you the weight and bias. So in this particular case, what you're basically learning is the slope W and the bias. Okay. I'm doing a simple binary classification under the assumption that the 2 classes can be separated by a line. Okay. So in this case, the slope of this W that you would learn would be negative, and the offset would be around this point. Now, you would be able to appreciate why we need this B. With just a W, all you can change is the slope, right? So slope of this line. But oftentimes, you would like to put an offset. Where should I put the slope here? Should I put this somewhere here, or should I put this somewhere here? So B allows you to give that flexibility to appropriately place this straight line. That is basically the role of the intercept. If you recollect the equation of a straight line, it has y is equal to mx plus c for one dimension. M is the slope, c is the intercept. B is playing the role of that intercept to appropriately place this line. Everything on one side of the line is belonging to one class. The other side of the line is belonging to other class. Now, by looking at the training data, what we're figuring out is the slope, right? M, or this W for higher dimensions. Once you figure this out, you get a test case where the inputs are basically 2 features, right? So petal length and petal width. For the test case, suppose for that particular instance, petal length is 2 and petal width is 0.5, then you would be somewhere here, right? So 2 and 0.5, then you can make a decision, okay? So perceptron function is basically figuring out what this W's and B's are when you call this fit, okay? So perceptron is basically doing TLU of X, W plus B. When you call a fit, it's going to learn this W and B. Once you pass that as an input to the prediction, it is going to give you a class label. So in this particular case, for 2 and 0.5, it is going to give you as Iris setosa, okay? So now, this is for a binary classification, but a lot is going on here. First thing, we are assuming that the data set that we have is linearly separable. That means I can separate that with a straight line. What if the data set that we have cannot be linearly separated? I cannot simply draw a line to separate, right? So that it requires a complex decision boundary. Further, I'm also assuming in this particular case with a single output that I'm not doing a multi-class classification. It could be that if I want to do a multi-class classification, then maybe there is a further class where you would like to draw one more line, or you would like to distinguish, or this is another line that is going to differentiate between this the three classes that we have here, right? So this versicolor, Virginia, and Setosa, right? So if you want to further, you might want to do again another linear classifier, but most of the examples might not have this linear separability. Now, can we get a decision boundary that is more intricate? How do we do that? So the main take-home message is the TLU, the single layer TLU that we had so far, is capable of outputting decision boundaries that are linear in nature. Okay, so that can be used for classification for classes that are linearly separable. Now, when does this not work? That basically helps us to ask this question, also to help us deviate from the limitation of logistic regression, for instance, or linear regression, with which there is a lot of similarity to the discussion that we had so far, except for the nonlinear operation via the step function, right? So the TLU is doing that nonlinear operation, but in linear regression will not have that, but now we have it. So suppose you have a classification problem, which is called as this XOR classification, a classic textbook example, where linear separability does not hold anymore. So in this particular case, we have two classes, right? So the squares, the filled squares and the triangles, and now to separate them, XOR basically means that whenever you have unequal inputs, 0, 1, you get a 1 output. Whenever you have equal output, 0, 0, and 1, 1, you get a 0 output, right? So that basically is the class output, which basically means that the triangles belong to one class and the solid squares belong to the other class. So in this particular case, we cannot simply use one single line to separate the classes. We require a more complex decision boundary. Okay. Now, how do we achieve this? But still with the same philosophy that I would like to linearly combine my input data and non-linearity. Okay. So I don't want to deviate. I don't want to introduce any new heuristic, but still use the concept of artificial neuron inspired by a biological neuron, which is basically an implementation, which is linear combination plus a bias and a non-linearity. With that, I would like to achieve this complex decision boundary, which is not beyond linear separability. Now, to do that, what one would do is, instead of what we did so far was a single layer. Now, you could, in principle, achieve this complex decision boundary by stacking different layers of perceptrons, one below the other. So we had a single layer of TLU, single layer of perceptrons. Now, what we will do is we will vertically stack one below the other, which means that we are composing several nonlinear functions. Okay. So that brings us to what is known as a multi-layer perceptron. So linear regression perceptron is basically, this unit is called as a perceptron, right? So it basically takes a weighted combination and gives you a 0, 1 output. Okay. So this unit itself is called as a perceptron. Now, a single layer of perceptron, you have many such units stacked one next to the other. Multi-layer perceptron, we'll see what that is. Linear regression is a task. Okay. So perceptron, you can use perceptron to solve a linear regression problem or a logistic regression problem or any other problems, as we will see throughout this module. Regression is one such task. You can use this model to achieve that task. Okay. So this is basically a compute unit, right? A compute proposition where you are linearly combining and maybe with a bias term, right? So that is what is a perceptron. Okay. So this is a perceptron unit. Whatever input you give, I can compute an output given W1, W2, W3, and B, right? So for a three feature input. If you have multiple features, you have multiple combining weights. So how to use this module as a Lego block, right? So you would like to use this as stacking vertically, horizontally, etc., to achieve a particular task, which is a linear regression or a classification task. Okay, so that is the basic difference. Now, for TLU that we have discussed so far, the nonlinearity function phi, we limit ourselves to a step function. Okay, we will see as we progress what can this, how different can this be. Now, a multi-layer perceptron, as I was mentioning, is basically a stack of single layer perceptrons, one below the other. Okay, so to see that we can achieve this XOR classification via a multi-layer perceptron, let's take a look at this hard-coded example where we see that for a particular choice of weights, we indeed achieve an XOR classification. Okay, so here the weights are figured out, right? So there is some algorithm to figure out what these weights are, and those are written here. So the gray arrows have weights of 1, okay? And the red arrows have different weights that are mentioned on top of this. So now what do we need? We don't have a single layer TLU, we have a multi-layer TLU. This is the first layer, hidden layer, or the first layer, and this is the output layer. Okay, so now what we are doing is the following. Suppose we can do this exercise for remaining outputs. Maybe you can do this. I'll do it for one particular case. So what we have is a 0, 1 input. What we expected the output is a 1. Now you have 0 times 1. So all the gray arrows have a weight of 1, recollect. So 0 times 1 is 0. 1 times 1 is 1. And a bias of minus 0.5. So what we get is 1 minus 0.5, which is a 0.5. This will trigger an output of 1, okay, at the TLU. Similarly, for the other case, what we have is uh, a 0 plus 1 minus 1.5. So that is basically a 0 at the output. So you can do this math and then you see that the output is 1. So what we are basically doing is we are stacking multiple nonlinear functions that would help us to achieve this XOR classification. So similarly, you can do this exercise for 1, 0, 0, 0, and 1, 1. You would see that you would implement this classification. So what the simple example basically illustrates is that now we can achieve a classification beyond linear classification. Okay. And there exists certain weights. Whether our algorithm is going to figure out these particular weights and biases of minus 0.5, minus 1.5, etc., that's a different issue. But at least we know that an optimal algorithm, if there exists, should figure out these weights and help us achieve this classification or XOR classification that is computing this complex decision boundary, which is beyond a one linear line. Okay. So what we have now is a stack of single layer TLUs, which we call as multi-layer perceptron. Perceptron, you have multiple layers of these perceptrons. Each layer can have many perceptrons. You have multiple such layers. As the obvious name would suggest, it is called as a multi-layer perceptron or an MLP. Okay, it is a feed-forward network. The information is flowing from input to the output. You're basically doing a linear combination of the input, adding a bias. The next layer would basically use the output from the previous layer, do a linear combination, add a bias. You keep on repeating the same. Okay, so yes, Pankaj.
In the previous slide, Professor, what is the function assumed for the TLU? Is it a sine function or any
It
other
is a
function?
step function. So far, if I don't say anything, it is a step function. So, for example, what we saw in this for this particular neuron, the one that I'm trying to shade here, the output would be, the input would be a -1, so the output would be a 0. So it is basically this step function, which gives for all positives, it's going to give a 1 and give it a 0 for all values less than 0.
Thank
Okay.
you. Thank you. Yeah, thank you.
So again, I'm seeing many questions in this Q&A. Very likely I'm missing this. Please use the chat window to type those questions. So Prasad Rao, the number of TLU layers will vary depending on you have a multi-layer, multi-label, multi-class, or a binary classification. See, in this particular picture that we are seeing in the slide, we have a binary classification. So the output is a single output, 0 or a 1. In some cases, we require an output to be of this form, right? So the output, it could be like 1, 1, 1, 0, 0, 1, 0, 0, right? So this could be an output. In this particular case, we require 2 TLUs at the output. In multi-class, you can have either of the n classes. So that also requires n outputs. So it depends on the outputs. The number of output TLUs depend on the task at hand. Okay, so now let's try to put these thoughts together and see what is a multi-layer perceptron. So multi-layer perceptron, as I was telling, it is a stack of multiple single layer TLUs. So the intermediate layers are called as hidden layers. You have an output layer. The number of outputs depends on the task at hand. If you have a binary classification, you just have one output. If you have a multi-class classification, you have multiple outputs. The input to the first layer is a linear combination of the features. So you do this computation. So compactly, I can write the output of the first layer as XW1 plus B1. Okay, so this is going to give me, say, Y. This is what we get at the first hidden layer. Now, the final output in this particular cartoon illustration will be Y2. So whatever we did previously for the first layer, I take a linear combination with the weights and a bias, I get an output. Now I treat that as my intermediate, I treat that intermediate output as an input to the next layer. So all the weights that are here, so there are biases, okay? So for TLUs in the hidden layer, I get 4 biases in B1, okay? Similarly, there are 3 biases at B2. The remaining ones are the weights that are the arrows that are sitting here, right? So those are the weights. So that is W1. Similarly, the other layers will also have the weights, okay? So what we have here is, in particular, we have 2 inputs, one hidden layer with 4 neurons and 3 output neurons. The bias doesn't usually combine with the input, so it always outputs the input is 1 to a bias, okay? And the bias we have to learn. Depending on how many layers we stack, we have those many weights and biases that we have to figure out. More generally, I can write whatever is going on as a composition of several nonlinear functions. So this is my final output, okay? So now you're seeing that I have a more complex architecture compared to a linear regression or a logistic regression loss function that we were using in the ML module. I have now a nonlinear function as a hypothesis for my class label, okay? In particular, I have more complicated nonlinear function, which is a composition of linear combination plus a nonlinearity, okay? And the information, as I said, is flowing from input to the output. Hence, this is also called as a feed-forward neural network architecture. We will see when we are discussing the recurrent neural network module, there is a feedback also. Right now, we don't have any feedback. It is a feed-forward neural network architecture. And if you get multiple layers, if there is no hard-coded number to it, if the number of hidden layers are, say, 2 or more, here you have 1 hidden layer. In case you have 2 or more hidden layers, that is called as a deep neural net because you have a deep stack of hidden layers. It is called as a deep neural net. When is it deep? Doesn't really change. I mean, when is it called deep? Some people call it deep when the number of hidden layers are 4, 5 more. But in general, if you have only 1 hidden layer, it is a shallow network. If you have multiple hidden layers, you have a deep stack of these perceptron layers, which is called as a deep neural network. Okay, so there's no particular number that, okay, you require these many hidden layers to call it a deep neural net, but that's how the name deep comes from. Multi-layer perceptron is a deep neural net. Multi-layer perceptron is a stack of multiple single layer TLUs. Okay, and to learn these weights and biases associated with each of these layers, as I was telling, this layer also has weights and biases. This is what we had before. Now, repeat the same thing, but you now have a different set of weights and biases, W2 and B2. So learning all these weights and biases, say, suppose you have 10 layers or 15 layers, then learning all these basically is called as deep learning. Okay, I hope that is clear. Now, as you can readily imagine, whatever exercise that we did before to hard compute the gradients for a single layer, it's not viable anymore, right? So I have many layers. Whenever you see a neural network architecture having a billion parameters, that means that I'll have to do those gradient computations for a billion of those parameters, which is clearly not possible to do, right? So now the question is, how do we do that in practice? Apparently, people are training these chat GPT models with a billion parameters without somebody computing those gradients. So there should be a tool to do that. In particular, what is the tool? How do we achieve that? We will see all this as we progress. Now, the basic idea here is that I have a stack of multiple layers of neural nets. I mean, multiple layers of single layer TLUs, which we call as multi-layer perceptron. Now, let's try to understand a bit more in detail the number of parameters for this cartoon setup that we have. So, as before, suppose our data is n times p. N is the number of examples, p is the number of features. Always keep in mind, W's and P's do not change from one example to the other. We are going to learn the W's and D's that fit all the examples that we see. Okay, so it is not changing per example, but for the entire training set, we will figure out what are the features that are important. Those are the combining weights, right? So figure out what are the features that are important to result in a particular task. So now what I was already writing. So this was the step function. In the first layer, this is the output of the hidden layer. We have our data. I linearly combine with W1 and B1, which are the weights and biases of this layer. Okay. Okay. So now what that basically means is my data matrix X is n times P. W1, as we saw before, this will be P times the number of outputs or number of hidden neurons. In this case, we have 4 hidden neurons. Okay. So W1 is, in our case, it is, we have 2 features. Okay. And 4 output neurons. So this will be 2 times 4. B1 would be, in our case, 4 times 1 vector. Okay. So the first layer, you already have 8 plus 4, 12 parameters to learn. Now, you get an intermediate feature. This is also called as we had our initial feature matrix. There is an intermediate feature matrix, and this would be n times 4. For each example, I now transform these 2 features that we started to 4 features. Those are the outputs that we get at each of these layers. Okay. Now I treat that as my new feature combined with W2, which is again, as before, number of features at the hidden layer times the number of output layers. Okay, so in this particular case, we have, this will be 4 times 3. Okay, and similarly, B2 would be 3 times 1, the number of output neurons, right? So that basically helps us to figure out, this is our final output for this cartoon illustration, right? So with 2 features and 4 neurons in the hidden layers and 3 output neurons, because we are looking at a 3-class classification, for instance. So sigma is that step function that we have been using so far. Okay. So again, this will be n times 3. So for each of the n examples, I get 3 outputs. Okay. So H is now n times 4. This is 4 times 3, and B is basically 3 times 1. Okay. So I hope this is clear. Any questions so far?
Professor, can you repeat this? How we have calculated this weights and biases for different layers?
You mean the dimensions?
Yeah.
Yeah. Okay. So we have not yet computed the entries, what goes into W's and B's, that we have not yet computed. That is what we will discuss as we progress. But for now, what we have basically done is that what do we know with this? We know our input data has P features. Now I need to combine these P features linearly. So clearly W1 will have P times something. Now, how many hidden neurons do we need? Or how many hidden layers do we need? That's a hyperparameter. Okay, that is flexible. Now, suppose we have, for this illustration, we have chosen that we require 4 hidden neurons and 1 hidden layer. You can have multiple hidden layers as well. But for now, we are choosing 4 neurons in the hidden layer. So that basically determines the size of W1 matrix. So that will be P times 4. And as we saw before, each of these 4 neurons would get 1 bias input, that is giving a size of 4 times 1 for B1. So W1 is 2 times 4 because we have 2 features and 4 neurons in the hidden layer. We have B1, which is of length 4, because that is what is feeding to those 4 neurons. Repeat the same for the second layer. I have now 4 features that is becoming 3. 4 is becoming 3 here. And I have 3 inputs as biases, so that is 3. Okay. And for now, we are assuming that all the neurons in the hidden layer have the same nonlinearity of step function. Okay. Is that clear?
Yeah. Thanks, Professor. Thanks.
Yeah. So now what is also apparent is that more deep we go, we have more number of parameters, right? So now just with this single hidden layer and a minimal of 4 neurons, we see that we already need to compute how many, right? So 8 plus 4, that is 12. And then 12 plus 3, that is 15, right? So 12 plus 15, 27 parameters is what you need to compute. Okay, so now let's take a moment to reflect what we have been doing. And let me see if I can put this poll question and yeah, I hope you're able to see the poll questions. To quickly recollect what we have been discussing, so you can self-reflect while we pause for this poll question. I'll end this poll in a few seconds. Again, throughout this lecture and throughout this module, I'll be pausing with poll questions for you to self-reflect, gather your thoughts together. The goal, of course, is not to grade based on if you get a correct answer or not, but do participate. That is more important in these polls, so that I also kind of you can use that as a feedback to see if, okay, I need to reiterate on a few things. And I also see that, yeah, I'm not talking to just a screen, and there are people who are really listening to me, right? So always important. Okay, so I'll end this poll now, and happy to see that the majority of you got it all right. Again, the goal is not to get the right. Of course, I mean, right answer is always better, but participation is also more important. I see that, okay, there are like about 140 people, and yeah, if at least like 70% of them answer, then I'm happy, right? And 70% of them get the correct answer, I'm even more happy. Okay, so as I was already telling, for this simple neural network that we can put nicely understand what is going on, you have 27 unknowns, which means that we'll have to compute those 27 gradients, right? And 27 gradients, you have to have a mechanism to figure out this update rule so that we obtain what these 27 numbers are so that we can deploy this neural network architecture. Now, maybe for the application at hand, you don't have a network that requires only 4 hidden neurons, but you require, say, 100 hidden neurons, and you require 5 hidden layers, right? So, and then you have like about 100 features. Now, with this simple exercise, you can extrapolate the number of parameters that you require, and also maybe help yourself visualize when people are talking about chat GPTs, etc., that require a billion parameters, right? So you would be able to understand what is the size or the architecture of the neural network, at least visualize at this point, the scale of the problem that we are dealing with, okay? So we did this already, right? So we have like two becomes 4. So that's why you have 2 times 4 and then 4 inputs, that is 4. You need to add all this, 4 becomes 3. And we have 3 bias terms. So that is why we have 3. So in total, you add all this, do the simple math, you get 27. In fact, as we will see later, you don't have to even do this math. There are simple commands that you can invoke to give you a model summary that will tell you what are the number of parameters. Yeah, it is just so 3 times 1 or 1 times 3. It's a convention to treat all the vectors as column vectors, right? That's why we say 3 times 1 and not 1 times 3. But what is more important is that it's a vector that has 4 coordinates, right? 4 entries and 3 entries, B1 and B2 accordingly. So bias is not taken as 1. So the input to the bias is taken as 1, right? So here, if you look at any other neuron, it will be x2 times W. Here, you can treat this bias as an additional feature, but that is always 1, okay? But the value of that parameter, right? So what is the value of this arrow? B1, B2, B3, that is still unknown. So that has to be trained. Okay, I hope that is clear, Pankaj. So whenever we say, so the way you should see this again is like x1 w1 plus x2 w2 plus b times x3, but this x3 is simply 1, okay? But still, what is that b that we have to figure out, right? So that is still to be learned. Okay, now, obviously you can question that why do we require this non-linearity, right? So apparently I have been stressing so far that we require a threshold logic unit that requires the step function. And also we can learn these complex decision boundaries if I have a composition of several of these nonlinear functions. But now we see that this nonlinearity plays a crucial role with the simple math that we have here. So I have 2 functions, f and g, with 1 feature, right? So x is only the feature. So you have like combined with 2 and the bias is 3. The next layer, the weight is 5 and bias is -1, right? So this is a simple function. I'm now composing these 2. There is no non-linearity here. It is 2 linear functions, right? So f is linear, g is linear in x. I'm composing these two functions. What that means is I multiply 5x minus 1 with 2 and add a bias of 3. What I get is again a linear function, which means that if I compose several linear functions, I again get a linear function. So this can indeed be written as some other linear function h of x. But the moment I add nonlinearity, I cannot basically express composition of several nonlinear functions as one nonlinear function, right? So that is the main point of having nonlinearity. That is what deviates from all the traditional ML tools, including linear regression models that you have been seeing so far with deep neural nets. So we have composition of several nonlinear functions. And what is also very interesting, a nice theoretical and an important groundbreaking result back in time is that when you stack several of these nonlinear functions for a large enough or a deep enough multi-layer perceptron that is with many hidden layers, you can in principle approximate any function that you would like, any complex function. And that result is known as universal function approximation theorem. I'll not go through that theorem, so you don't have to be worried about understanding the underlying math. But if we have deep enough layers, you can approximate any decision boundary. So suppose so far we were thinking still of a simplistic case of an XOR decision boundary that is some slightly more complicated than a linear one. But imagine that your class labels or the classes are of this form, which requires an even more complex decision boundary, right? So any decision boundary can be approximated with a deep enough feed-forward neural network or a multi-layer perceptron, and hence deep neural nets are very powerful, right? So all we have to figure out is now a way to train these neural networks. We will see that next. So just to quickly summarize what we have been seeing so far, we started with this artificial neuron that was hardwired. Any logical proposition can be implemented, but we needed some adaptability. I need to change the output based on the input. So the simplest way to do that is to take a linear combination, right? That's the simplest function that we can think of. Take a linear combination or an affine combination, have a nonlinearity. We saw that with that we could achieve basically a line which separates the two classes, or a hyperplane more generally. So the classes should be linearly separable. Now, all data sets need not be linearly separable, or tasks should require function outputs from a model which is more complex than simply a linear separation. A linear regression or a logistic regression would require a linear classification. This requires more complex decision boundaries. So that can be achieved by stacking multiple layers of a single layer threshold logic unit, and that we call as multi-layer perceptron. We saw why is having this nonlinearity at each layer is important. If not, then basically all these linear layers can be collapsed into a single linear layer, which is again implementing a line, right? So now the question is, we have figured out what this W's and B's, how to put this together for any arbitrary size network we want. We also get a sense of how many parameters we require. Now the question is, how do we train such neural networks, right? So that is what brings us to how do we implement this in practice, okay? Okay, so that brings us to the training of S. Jayanti.
Professor, the nonlinear function which was phi or sigma, those are step functions in case of single layer perceptron, and
All for now it is step function,
okay,
right?
even for nonlinear.
So step function is a nonlinear function. So that is the same function that we apply for each of these neurons that you see here so far.
Okay.
Okay. So later on, we will see that, okay, it's not necessary to limit ourselves to a step function. This was the nonlinear function that was initially conceived. Later on, we'll see what is the limitation of that.
Yeah.
And then we will introduce more amenable nonlinear functions.
Okay, and the previous slide where it was shown f of g of x, that's different from the step function.
Right. So here there is no nonlinearity. The message
Okay.
of this is that if you stack multiple linear layers,
Okay,
it is of no use,
understood.
right? So basically, although I have two linear layers, it can be collapsed as a single linear layer.
That means f of x as well as g of x will go through a step function in this case.
So far it is not, but I mean here f of x composed with g of x, I can write it as h of x, which is a linear function. But
Okay.
now suppose I had something like this. This is, say, I call it as, say, f1 of x,
Yeah.
or I should call it as g1 of x with nonlinearity, and f1 of x is, say, nonlinear. So basically, what we had here, there's no sigma, right? So
Yeah.
now suppose I would like to do f1 g1 of x. So this is composition of nonlinear functions. This
Yes.
cannot be written as some sigma times something, which is
Yes.
some h1 of x, right?
Yes.
So I cannot basically collapse it as one nonlinear function.
Okay, thank you.
That was the main message.
Yeah.
Okay, so now let's proceed with the training of MLPs. By the way, a quick heads up. So today we'll be winding up at 12:40, right? So I might require 10 more minutes. So 12:40, just count for that already. So training of MLPs. So now we have set up this multi-layer perceptron. There are weights and biases. Now the question is, how do we figure out? Clearly, if I have even 27 parameters, there is no way I can hard code the gradients, right? So there should be an automatic mechanism to basically make this work. Okay, now the question is, what is the procedure? We'll understand the procedure. So the procedure itself involves the following steps. Before that, let's quickly understand through this cartoon what a semi-supervised learning is, a quick recap. So in semi-supervised learning, you have examples and associated labels. In this case, it is classifying an email as a ham or a spam. So it has a label 0 or a 1. That is your training data. You would use this training data. There will be a new instance, a new email comes. We'll have to figure out if it is a ham or a spam. Okay, that is our prediction, right? So simple simple supervised learning task. Other example is this digit classification, where we have in our training data several handwritten digits. Okay, each one is 28 by 28 pixel. And the pixel intensities are grayscale images. So 0 to 255 is the input feature. Okay. Now, corresponding to each of this digit in our training data, we have the digit number. So it is 0 to 9, 10 digits. In this particular case, in the training data, we'll have a 1, right? So what that means is, so this will be the label that we have for this particular digit. Okay, for now, each of such digits, we have a 10 length binary vector, which has only one non-zero entry, right? So that is our label. Okay, so now we have this as an input data. Now the question is, how do we figure out what are the weights and biases of our neural network? Now to do this, the procedure that is often followed is the following. Suppose we have training data. So this handwritten digits, we have 70,000 of these images, okay, in our training data. So you split that training data into test and training. Okay. So suppose we say out of 70K, 50K is what I would use for training. Test is something that we never use during the training process. So it is not used for learning W's and D's. Now this 50,000 examples in the training data, which means that you have 50,000 images and the corresponding labels, which are these 10 length binary vector. Okay. So now we divide this 50,000 into small chunks called as mini batches. So typically 32 sized. Okay. Now every iteration we work with 32 examples. Okay. 50,000 is our training data. Test, we never use this for training. It is once the model is learned, once your W and B's are learned, either you deploy the model or for reporting performance, you use the test. Training is divided into smaller chunks of 32. For instance, 32 could be 50, but 32 is the number that I'll be using. And you would be cycling through the training data using 32 samples each time. So one iteration, you would use 32. Next, you would go to the next 32. You would complete everything. And then once you complete everything, you go back to the first one. So one pass through the training data, visiting one mini batch at a time, is called as an epoch. Okay. So one pass handles a mini batch at a time, and you pass through cycle through the training data one mini batch at a time. So that is your epoch. Okay. So what we have done so far is that I have this training data. You divide that into smaller chunks. Each chunk you process. Okay. How we process, we will see as we progress. Okay. So now the second step, it is forming data. Okay. Second step is the forward pass. So I have not trained anything. What you will now do is you would start with some initialization of weights and biases. Say iteration 1, I would randomly choose some weights and biases, right? So you draw randomly the entries of W's and B's. So we know the matrix, say 2x4 and 4x3 matrix with random entries. I populate that with random initial entries. Once I have that, I know how to compute the value at the hidden layer and the value at the output layer. Because I know, if I know W and B, the features X is known. All I need to do is do this matrix multiplication and apply this nonlinearity. I can compute what H is. Once I know H, I can redo the procedure, compute what O is. Okay. So for each of these examples in the mini batch, so this will be 32 times in our example again, this will be 32 times 4, and this will be 32 times 3. Okay, so that is how we could do a forward pass. If I know the initial values, I know the values of W and B, I can compute. Now, for certain initial value, for example, in this cartoon, you would see that the 8th output that is of interest for that particular example in the mini batch, the output is 0.7. The remaining outputs are close to 0.1 or 0. Now, our goal is to record this error and make sure that error goes to 0, which means that this 0.7, I need to make it as 1. The remaining outputs, I need to bring it to 0. If I do that by passing through the data in each iteration, then I'm minimizing the error. Okay. And maximizing the performance, accuracy, and doing so, I'm training the network. Now, to bring this 0.7 to 1, what do I need to do? I need to go back and change all the weights that were leading to this 0.7. So the input X is given to me, right? So that's basically this pixel intensities. 28 times 28, what I feed here is 28 times 28 is 784. So you basically vectorize that image, right? For this toy example, we can do that. 784 inputs. It has numbers between 0 and 255 that goes as an input. Okay, I compute the entries at the hidden layer and then finally at the output layer, I record. So now I need to go back, and that is called as back propagation. We need to back propagate this error to bring this 0.7 to 1 and remaining entries to 0. What is in our control is to change the weights and biases so that the output at the 8th location becomes 1. Yes, Shibani.
Professor, one question. When you say that the error you are making it 0.7 to 1, why 1? Because we are ensuring the error to be 0, right? Not 1.
No, the output 0.7 should become 1. And because it's digit 8. So we want at the 8th location 1 and remaining as zeros. So we start with an initial number for W and B, and I simply
Okay.
measure what is the output by doing this matrix multiplication. I get a 0.7.
Okay.
Now, our goal is to make this 0.7 a 1 so that the error becomes 0.
Okay, that's what I'm failing to understand how the error will be 0 if I make it as a 1.
Yeah, because
Is
what
yeah.
so what is the for this digit 8,
Mm-hmm.
the vector that I desire at the output is this vector,
Yeah. Okay.
right? So that
Mhm.
an entry of maybe 1 here and remaining all zeros, right?
Yeah. Yeah. Okay.
Yeah.
Okay. In that sense, I was okay.
Yeah.
Okay. I
So
got you.
now the first pass that I got was giving me a value of 0.7.
G7. Yeah.
Yeah,
Okay.
and that was a consequence of certain weight choices that we made here.
Mm-hmm.
Right now, so what that basically means is that I need to now fine tune. For example, say, let's go back to this picture. So this was already giving me a weight of 0. I mean, output of 0. So that means that I don't have to worry about these weights.
Yeah.
All I need to worry is about these weights so that this 0.6, I mean, the output of 6, that is
Become
0.1,
0.
hopefully reduces further.
Hmm.
8 hopefully increases. So I need to worry about only these weights.
Yeah.
Okay, so now what that basically means is that I have to, in the next iteration, I have to propagate this error and change something so that the 0.7 becomes a 1 and so on. Okay.
Okay. Got you. Thank you.
So now, yeah, so this is, I mean, I'm just telling this for one particular example in that mini batch. We need this to hold for all the examples in my training data. Okay. So that is what every iteration would bring. So the error would not be maybe 0, but it would go close to 0 is the hope, right? So to figure out so that the error goes to 0 on average for all the data points, right? So that is what we expect as iterations progress. Okay, versus epochs, this is what we hope for. You're doing something, you're doing some magic is going on, and that magic basically is gradient descent algorithm that is kicking in to basically refine the weights so that the error goes to 0 as iterations progress, right? So in that process, we are in step 2, where I first get an estimate of the error for the current choice of weights and biases. Now, the third step is where the magic happens is the backward pass. In the backward pass, what we are basically doing is, as I said already in English, you are refining those weights by measuring this loss. Okay, so how should I change my weights so that the loss becomes 0? Okay, so that is the gradient of the loss. So now, like the simple derivation that we did, we are doing this. So you update iteratively the weights by solving this gradient descent method, you're measuring the loss discrepancy between what you desire and what you have. And how should I change my weights so that the loss decreases, right? So every time, that is our goal. And this gradient update will eventually result in a behavior like this, okay? But what you need to keep in mind is who is computing this gradient for us, right? So clearly, when you are asked to code a deep neural net, you would like something that is automatic and not this cumbersome that somebody is computing the gradients for you, right? So now what we will see is there is actually an automatic procedure to compute this gradient, and we will see that next. But before that, just a quick recap of this optimization question. So actually what we do is called a stochastic gradient descent, right? So why do we require mini batch? Why do we require stochastic? And what is gradient descent, right? So that is helpful through this picture, and also help us to understand the recap the optimization part. We'll be very quick with this poll, maybe 45 seconds. I'll end this poll now. Okay. So with this, I would like to convey the message of doing this mini batch, right? So what we are actually doing is we are evaluating the error on a small chunk of data, okay? So small chunk of data, why do we want to do that? Because what we have is a limited memory, GPU memory. When we are evaluating the gradient, it doesn't make sense, although desired, it doesn't make sense to put all data at once in the memory. Okay, so that is what you would do ideally, right? So 50,000 samples, let's compute the gradient with respect to all those 50,000 samples at once, and then do a gradient descent. That is what is the smoothest trajectory here. The gradient descent is going to go towards the minimum, right? So that is that single line that we see here. Now, we don't have access to the entire data. For example, imagine that mini batch, although not desired, has only 0 digits. Now it's going to figure out a neural network that's going to do only 0 classification. In the next batch, you're going to show 1 digits. Although that is not desired, you require a right mix of the data sample. So you shuffle and then give it as input. The other extreme is I process only 1 sample at a time. So first time you figure out the weights and biases for the first sample, which is 0. The next iteration, you figure out the weights and biases for the next sample, which might be 9. So every time you're changing. Now, between these two extreme worlds is the mini batch, which is going to give you the trade-off between the trajectories, like what we see here. One is giving us a smooth behavior to the minima. That is where the optimal point is. The other extreme, which is the 1 sample at a time, is giving us a very noisy behavior, which is never going to converge, right? It's always going to hover around the input. The best out of 2 worlds is the stochastic, which is less noisy compared to the one sample, that is stochastic gradient descent. What we use is normally the mini batch version of the stochastic gradient descent. Okay, so now there are several ways to pick optimizer. If you look at Keras, there's basically a lookup table to pick different optimizers, which are variants of the stochastic gradient descent with several tweaks. What is popular is known as this Adam optimizer, Normally, if you look at an optimizer, you would choose an Adam optimizer. You can very well use SGD. We will see as we progress, maybe in the next lecture, how to code this for an MLP classifier or a regressor, right? So I will again come to that point in the next lecture. Yeah. So all these operations are happening in GPU memory. So when I'm training a neural network, I only load a part of the sample which is required for computations to the memory. Now, if I choose a mini batch that is small, then I require a smaller GPU memory. Of course, it depends how big each sample in a mini batch is, but every time you only need to load that. Next, you remove that and load a fresh chunk of data. So that basically limits the size of the memory. Now, if I want to process all the data at once, 50,000 samples, you require a very large GPU memory, right? So more GPU memory is always expensive, right? What we can typically afford is a GPU memory maybe of 20 GB or 48 GB, depending on how much money we can pay for, right? Okay, so now how do we learn this gradient, right? Clearly, I don't have a manual computation capability to compute these 27 variables, gradients with respect to these 27 variables. So to that, an automatic procedure is used in the backpropagation is the following. Recall, we have to compute the gradients. And to compute the gradients, if you recollect, very nice, otherwise it is okay. Maybe from +2, you might remember what is known as chain rule. In all these MLPs, what we have is a composition of several nonlinear functions. F1 composed with F2, F2 composed with F3, and so on. Now, whenever we have a composition of functions, if you want to compute the gradient of the output, the loss function, with respect to some of the variables, then chain rule tells I can first compute the gradient with respect to the second function, as we see here, and finally the third function with respect to x. And also, what is interesting is, if to compute this particular gradient, it doesn't matter if I compute this product in whichever direction, forward or backward direction. And it so turns out in a very interesting way is that if I compute this differentiation in a backward way, I can form a computational graph that requires only 2 passes of the data to compute this gradient. That we will see that with a simple example of least squares cost function. Okay, so what we see is an automatic way of computing the gradient, which is a part of this backpropagation algorithm as we would like to have. So let's compute this loss. Suppose we have this loss function, which is basically, you might have seen this, it's a linear regression. And how do we automatically compute the gradient? For that, we form a so-called computational graph, like what we see here, where I'm basically breaking down the loss function into several ingredients. What I would call the loss function is D. It's a squared loss, D square. How is D made up of? D is made up of difference of 2 terms, Y minus V. V is X transpose W. Okay, so I start with X transpose W, I do this difference and square. So I have 3 basic units. Now, we start with this computational graph, which says I have X and W with me. I can form this product, X transpose W. I have Y. So this is a label that I have. This is my input feature. This is the intermediate W that I have. I have this computational graph. I combine X and W to get V. I take a difference with Y, I get D, I square. I get this computational graph. Now, what we can do is the following. This is the computational graph. Okay. So now to compute the gradient chain rule, what we should do is I need to compute the derivative of this loss function with respect to W. Chain rule tells I can do it as follows: differentiation of L with respect to D, D with respect to V, V with respect to W. Okay. So now I can form this computational graph and traverse through this trajectory. Okay. That leads all the way to W by simply doing this computation. So I compute the derivative of this with respect to this node with respect to this node, and finally with respect to this. So that is going to give me 2D, 1 and X. Eventually, now what I'll do is I will form a stochastic gradient descent to do this. Okay. Now, if I want to compute the value of the gradient, all I need to do is one forward pass. I know what is the value of W. I know what is the value of X. I know what is my label. I can do this forward pass to measure what is the loss. Once I have the loss, I know what is D basically, right? So I can compute the gradient. So basically with 2 passes, you can compute the gradient. Now let's try to do the same exercise for our MLP, but a super simplified one, where I'll assume that does not have any nonlinearity. The bias terms are 0. Okay. So now let's see what the computational graph would look like. With this idea, you can basically form a computational graph for any large neural network you have, right? So this is B2 is 0, B1 is 0. Okay. So now once you have this, you can form a computational graph as follows. I have the loss function. I have my output, which is W2H. In hidden layer is W1X. So I know what my features are. Okay. I know what the labels are. I can measure the loss. W1 is some intermediate weight that we compute. I multiply X and W to get Z. Apply nonlinearity to get H. Once I have H, I need to multiply H with W2. That gives me the output layer. Once I have the output, I can measure the loss function. Okay, that's a computational graph. Now, let's see how to compute the derivative with respect to derivative of the loss function with respect to W2, one of the weights, which means that I need to traverse this path. I need to compute the derivative of L with respect to O with respect to W2. So all I need is this particular function. Okay. So it's an easy way of computing the gradient. So now if I want to compute this gradient, all I need to do is I need to know what is W2, which I already know. I can measure the loss function and I can basically compute what is O. So I basically get the gradient. So similarly, we can do this for W1, for which I need to traverse this particular path. Okay. So if I want to compute now the gradient of the loss function with respect to W1, of course, I need to store X, W1, Z, H, O, L, and W2 to traverse all the way. But what is important to keep in mind is the following. This is again chain rule, right? Nothing fancy. But at some point, we'll see that I'll have to compute the derivative of this nonlinear function. That is, I need to compute the derivative of this nonlinear function, which means that to begin with, the nonlinear function should be differentiable, right? But now in our case so far, what we are using is this threshold logic unit, which is not differentiable at 0. Okay. So for that, the main change from the model from 57 to what is currently being used is to use a better approximation of this nonlinear function. For example, use a logistic function as a nonlinearity instead of using the non-differentiable step function. Okay. So what we now discussed so far is a simple way to compute the gradient via a forward pass and a backward pass. Okay. So doing this you can do this for any large network, and you don't basically have to manually compute the gradients. Okay. And this has been implemented in most of the deep neural net libraries like TensorFlow, PyTorch. You don't have to manually compute the gradient. Yes, Piyush.
So 2 slides back, you said backward pass requires only 2 steps, but forward pass requires as many as parameters. So how did we illustrate that difference?
So for example, if you want to compute the loss function, right? So you require a forward pass, which means that I need to traverse all the way. Let's use this example. The forward pass, if I want to compute, I need to store value of W, X, Y. And once this is there, I can figure out what this loss is. Correct? So that's the forward pass. I'm measuring what L is. For a given iterate W, given X, given Y. Backward, you're back propagating the loss. How are you doing that? With respect to each of this node in the computational graph, you're seeing how is it changing. You're doing dL by dt, which is measuring the loss, that rate of change of loss with respect to this path. Similarly, with respect to this and with respect to this. That is what each of these derivatives are telling us. So if I know what D is, I know that via the forward pass. I know what 2D is. I know what 1 is in this particular case. It could be something else, but I know what X is. So the backward pass or the back propagation is giving me the value of the gradient that I can use. But to be able to know what D is, I need to do that forward pass. Is that clear? So I need one forward pass and one backward pass, only 2 passes.
No, if you go back one more slide,
Mm-hmm.
The presentation deck, one more, please. Oh, yeah, so there it says turns out forward differentiation requires as many.
Okay. So
that's the difference. Yeah, those two.
So okay, so there are so this chain rule is a product of 3 terms in this case, right? Now I can compute the product in the forward direction or in the backward direction. Okay, so when you compute the derivative in the forward direction, that is called as a forward differentiation, that requires multiple passes, which we did not cover. What we are doing is a backward differentiation where I first compute dL with respect to dd, dd with respect to dv, and dv with respect to dw. That's the reverse direction, right? So I'm computing the first, the output change, next the intermediate. So I'm doing in the backward direction, and that requires only 2 passes. Okay, so forward differentiation, I did not cover what that is, but I can share I can point you to the material in Geron's book. That is there. What is the difference between, these are called as automatic differentiations, and there are 2 ways to implement this product, the forward and the backward. And backward is much more efficient.
Okay, thank you.
Okay, so now, so what we have seen is that, okay, for our model, we have to do a forward pass and a backward pass to traverse, depending upon whether we are computing the gradient with respect to W1 or gradient with respect to W2. Forward pass allows us to measure what is the output, and backward measures the rate of change per node in the computational graph. What is crucial is to recollect that whatever you do, the derivative will depend on the phi, which is the nonlinear function, and we need to choose something that allows us to update. Okay, that is very important. This is what I will also spend some time in the next lecture. But for now, let's take up this poll question to again wrap our thoughts around the back propagation. to basically understand what is the size that we need to allocate, get a sense of what we need to allocate to do backpropagation. What is obvious is that I need some memory to basically store the data. In addition to storing data, I require some more memory to enable all these computations. Okay, I'll end this poll now. Okay, so to get a quick sense of what is the storage required, to basically compute these loss functions in the forward pass, I require to store all these matrices, right? All these matrices vectors, and that is this number that you see here, right? So I require clearly to store the weight matrices for every iteration. I need to store the intermediate vectors, which are 4 vectors, x, h, z, and o, and then a scalar, which is the loss function, right? I need to store this for every sample in the batch. Okay, so now we get a sense of what is the parameters that we would have, what we need to store next to the data. Okay, so now this is backpropagation. Now what I will do is, before we end today's lecture, give a simple example, and then we will wrap up the thoughts so that you can also play around in the assignments, and we'll come back to revisit this in the next lecture. So I'll do this via, say, a regression task to see what this means. Okay, so again, beginning of the next lecture, Biraj will have many examples so that you also played around with these MLPs. Okay, so last 5 more minutes to wrap up this discussion, and then we can conclude today's lecture, and then we will continue discussion from this point in the next lecture after we know what to expect once you have played around with this examples. So recall MLP has a hidden layer, multiple neurons. Don't worry about how to choose the number of neurons, etc. You will have to go through that reading material. You will get a sense, but I'll again discuss that in the next lecture. So we have number of neurons. We have decided how many neurons we want. Okay, now what do we do, right? So for a regression task, let's assume that this is our simple task at hand, which is predicting the house price. Okay, what is regression? We have many features about the house price, for example, number of bedrooms, the location of the house, etc. We'd like to predict what the house price is. Okay, so now you have the labels for the training data, giving you an example of how the house prices are. Now you get a new house on the market. You should be able to predict the price of the house, right? That is regression task. Now, the way we would code this is as follows. In a neural network, in a Keras module. So you would simply stack multiple layers of these so-called dense layers with the number of neurons. Okay, so we would use 30 neurons, which means we have one hidden layer with 30 neurons. Okay, we'll go through this in the next lecture a bit more in detail, but just for you to play around in the assignment during the week, you can code this as multiple layers, with each layer having a specific number of neurons, and then finally you fit a loss function. Now, as you can see here, throughout this code, you will never see what is going on in the backpropagation, the computational graph. Nothing is seen, right? All you would do is you would set up this architecture, tell how many hidden layers you want, how many neurons you want in the hidden layer, and then what is the task you want to perform. And depending on the task, you would set up a loss function, a mean squared error loss function. Okay, so, and how you would like to compute the W's and B's via the optimizer. Okay, so use this as a template to play around for both classification and regression. We will revisit this more detail in a more detailed way in the next lecture. But once you do this setup, after the construction, all you need to do is fit the model. And what is going on at the back end is this formation of computational graph, forming the gradients, and then figuring out what is the value of W and B. Okay, so once you do that, you do a model prediction. So this is how simple it looks. Now, what we need to understand as we progress in the next lecture and further is how do we figure out how many neurons we need, how many outputs we need, what changes between a classification task and a regression task, and what are the additional details that we need to keep in mind. Okay, so that is what we will focus on in the next lecture onwards. Further understanding the code that is required, and also look at a couple of real world applications for classification and regression using MLPs, right? For example, if you want to put a bounding box, etc., what would change? So what we have done, to quickly wrap up, we have set up this construct of multi-layer perceptron, and then given a notion of how to achieve this training process to figure out what this W's and B's are without manually computing the gradient. So there is an automatic way. If this is a bit overwhelming for you, you need not worry, because whenever you're coding this, you'll never see that somebody has done all the hard work, and there is a backpropagation computational graph running behind that will help you compute the gradients, etc. All you need to call is the optimizer that would get you the gradients, run the training process. Now, what I would suggest is go through the remaining reading material, which we will revisit much more in detail. Take this one particular code snippet that is there for classification or regression, play around with that without any expectation of what is going on, how to figure out the number of neurons, etc. Just try to get a hands-on feel of this, and then we would revisit this. Once you have basically done this hands-on, you would be able to better appreciate what comes next. And then you will have to go back again to that code. And with that additional knowledge, you can again fine-tune your code, right? So that is what we will do in the subsequent lectures as we progress. Okay, so with that, I would conclude at this point and take up any questions that are there.
Professor, can you please explain this answer? I'm somehow I'm not able to. Yeah.
Sure. Okay, I'll do that. Yeah. So you mean the poll result, right?
Right. Yeah.
Yeah. Okay. So I've shared the. I think okay. I've shared the poll. So it's again related to our toy multi-layer perceptron. Recollect that the W is taking us from 2 to 4. So this will be of size 4 times 2. And W2 is taking from 4 to 3. So this will be of size 3 times 4. So those are the two matrices that you need to store in every iteration. Okay.
And we're doing backward propagation here, right?
No, so yeah, this is to compute the gradient, need to compute the forward pass. So, and backward pass, but for both these passes, you need these variables always in your memory. Okay. So now to do a forward pass, what all do I need? I need to first of all store W, X, which is 2 times 1. So that is that length 2 vector. So now I do 2 times 4 and 4 times 2, I get a Z. Okay, that is of length 4. Okay, so on. So that
this will be 4 times 1. Yeah, Z will be 4 times 1.
4 times 1. You apply a non-linearity point-wise. This will be 4 times 1. So that is this. And then this is now W2 is 3 times 4, H is 4 times 1, so this will be 3 times 1,
Correct.
and then
Yeah.
the loss is a scalar. So now the basic message from this computation is, whenever we are complaining that Colab is throwing us away, or I need to purchase a larger GPU, where is that requirement coming from? That requirement is coming from the size of the input data, that is X. You might have images, you might have these 50,000 training samples or 32 samples in a mini batch. I need to store all this, right? So in practice, you will not have 2 times 1, but you will have like 2 times 32 or 784 times 32 in our
Yeah.
example, right? So 32 examples in my mini batch. So this is what I need to store. And each point can be like occupy some 4 bytes or something, right? So now we can do this memory computation of to store all this data matrices with certain floating point precision. What is the GPU size that I need to set aside?
Yeah, so the matrices I understood, but the vector length you were saying, right? There are 4 vectors, 2, 4, 4, 3.
Hmm.
So this part only I'm a little bit confused. Scalar, I understood that will be the output.
So the 4 vectors. So X is a vector which is of length 2. Z is a
Okay,
vector of length 4. H is a vector of length 4. O is a vector of length 3. So those
Okay,
are the
okay,
4
got it.
vectors. So
Yeah,
I
yeah,
need
yeah.
to store all these vectors, right, to compute these intermediate operations.
Okay, so everything will be stored. That's what I was missing. Like those vectors
Everything,
will be-
everything needs to be stored,
Okay, okay. Thank
right?
you.
Yeah, because I mean, maybe there is a smarter operation, but like as you can see, like okay, if I have to compute Z, I need to store W and X. If I
Right.
need to store H, I need Z in my memory,
Mm-hmm.
right? But okay, I mean, this is for a toy example. We'll never do this computation, right? But you can basically get a model summary. We will see that code. I'll take you through the code in the next lecture, but
Yeah.
you will get a sense of what is that we are dealing with.
Sure, sure. Yeah, thank you.
So any other questions? Maybe I can go through. Harsha, you can unmute and ask if you're still around.
Yeah, Professor. So I was just thinking, like, okay, initially I understood. So each of the threshold logical unit is called a threshold logical unit, and when you go to multi-layer, we called it as perceptrons, right? Because it has multiple inputs and it gets into multiple layers, right? And when do we consider it as a neuron?
So see, neuron is a cell in the brain, right? So human or animals, right? So perceptron is something that makes this artificial neuron adaptable. Okay, so we are loosely using all these units as neurons.
Okay, okay.
So neurons, TLUs, and perceptrons are interchangeable, right? So
okay,
yeah.
okay, sure, yeah.
Okay.
Thanks, Professor.
Okay, Abhiraj. So in the next lecture, I will give more examples and applications, as well as a simple illustration to this pedagogical example of digit classification as we progress. I hope that's clear. Rupesh, is the derivative function?
Yes, Prof.
So yeah, so the derivative function, you see in this case, like you need to compute the derivative, right? So derivative, for example, okay, if you use a certain function, as we will see in the next lecture, certain functions, the derivative is known, right? So that is also, it's a computation that one needs to perform that is stored in the memory as well.
So
And
all those derivatives and computations are
right.
prefixed before training. Like before the training
the
starts.
derivative function call is
Yeah.
prefix.
Okay. So at each and every node, whatever the computation need to be done is prefixed before the, like it's well known. It is stored in some GPU
Correct.
memory.
Yeah, it is well known, and for that reason, it is often common to use the same nonlinear function for all the neurons.
Okay.
To keep it simple.
can you give a picture of like how when we give the
Mm.
data, like how behind the scenes that template is working,
Hmm.
whatever code template? Yeah.
Yeah, so the code template, see, I mean,
Like implementation part, like how the data is split to multiple GPUs, what data need to be stored, etc., if possible.
yes. So maybe I can, yeah. So I will do this anyway in the next lecture, but yeah, I can use the code that I showed. So here, what you would do is we should split it into mini batches, right? So it is not automatic. So we should split the entire training data into mini batches of our choosing, right? So I might have a larger GPU size. You might have an even larger GPU size. So our mini batch size could be different. So that is what we fix. Typically, we have only one GPU. We can have multiple GPUs. So whenever before we call this, we need to tell whether the code is run in a GPU or whether it is a CPU based. CPU, you can also process this in CPU, but it will take much longer time because of the architecture involved. So there is a line that we have to invoke saying that all these operations should be performed on GPU, right? And automatically the memory that will be consumed will be a GPU memory from that point. Okay. So we have to summarize, we have to specify the mini batches. We have to specify which GPU should be used and how many GPUs should be used. So that's a command line, a simple command that we have to invoke. And then yeah, so then the TensorFlow and the Keras kicks in, right? So to transport data from CPU to GPU, so that is through Keras.
Yeah, my question is exactly that. Like, is there any tutorial or some video where that Keras, how the data will be handled and the computation is done?
How
Any
the
some
memory, how the memory
yeah, not exact,
manage.
not only memory, like how the flow is happening, like how the Keras is handling the data between the GPUs and how the results are coming out.
Yeah, I don't know if they would. I mean, I think all these are like kind of proprietary, right? So I don't know if they it's a public know-how.
Okay.
But yeah, I mean, so this is like not just with Keras, right? So for example, like there is CUDA, NVIDIA that is also kicking in, right? So it's basically that API level detail we'll not go into.
Understood.
And yeah, and I think the memory management, yeah, it will be partly with this CUDA as well as yeah,
Understood.
Keras, how
Good.
the libraries are defined. So I don't know if they, I mean, yeah, maybe some of them would make it open, but not all.
Yeah, one additional question,
Yeah.
Professor. Like, okay, I'll get back.
Sure, I'll go ahead, no worries.
I'll get back. I forgot. I have written it somewhere.
Okay, no worries. No worries. Yeah. So, Sairam, we will go through image processing neural nets, a few architectures, but you would quickly realize that different architectures are small variations around the same architecture. So what we will cover is the basic architecture and how you can tweak one to get the other. So that will include ResNet, YOLO, many things, right? So, but the foundational architecture is what we'll focus on.
Yeah, Professor. Like can I ask?
Yes.
Yeah. In the collab, if whatever we take, we select the TPU and all. So, are we being allocated only one TPU or multiple? Like, may not be TPU GPUs.
I think only one and tiny percentage of that.
Okay.
Yeah.
So we may not be dealing with multiple GPUs handling and all.
Multiple GPUs, no. So multiple GPUs, you cannot do that in Colab from what I understand. So what we, I mean, you could basically load share tasks in multiple GPUs, but then you need
Hardware.
yeah, you need hardware, and then also there is something called as NVIDIA interface that connects the two GPUs.
So that is not available online as of now, like this Collab platform or any platform is not providing it. It is
Collab, I think
paid
the
maybe.
free version will not.
Okay. Okay.
Yeah, the free version, yeah, it will allocate. I mean, yeah, they don't even tell how they distribute the loads, right? Maybe
Okay.
they're using multiple GPUs, but that is kind of not transparent to us.
Okay. Thanks.
So Shanmuga Will Chandrasekaran, which topics we need to read in the ML book? So what we are looking at is the multi-layer perceptron chapter in that Geron's book. So that is what I'm using for today's content. So did I miss any questions? If people are still around. Tripti, this is training the model, right, with our knowledge. Tripti, are you still around?
Yeah, that question
Ah.
was when you were explaining when we chose number 8 and when looking at that number 8 has still the error, right, 0.7, and then we looked at it and we used our knowledge to derive that it is not right, and then we concluded that we are going to reduce it to, we are going to increase it to 1 and rest of them to 0. This is like we are training the model, right?
Yeah, so you have the labels, right? So you want to match to that label.
Yeah.
Yeah. So in a simple case, like suppose, I mean, so digit 8, we know that it is digit 8.
Right.
So now what we are trying to do is what should be the W's and B's that we should use so that if I show an 8, I get that 8 as an output.
On
Right?
that, I have another question. We decided, or we concluded that we are going to change weights of the steps which are not 0, right? So, and that ought to be 0. And those weights are also feeding into the steps. Okay, if you can go back to that one. It is. Yeah. So let's say like third step, it is 0.1 and we are going to make it 0. So there are weights that are coming to 3, and also from that, if you're changing those weights, they are also going to 4, right? So
Yes.
wouldn't it impact 4 also and make it not?
Yeah. So the goal is now to get the best set of weights so that ideally what I desire is I would like to make all of them zeros except the output corresponding to that number 8. And whether we can achieve that in practice or not, that is a different issue, right?
Okay.
But
Good.
now the direction that we pick to fine tune these W's and B's are towards that. So whenever we say that the loss should be minimized, that is what we are trying to do. And this is not just for one digit, but for all the samples in my training data.
Okay, understood. It's ideal. I mean, the goal is
ideally, I would like the loss to be 0.
0. Yeah.
But whether I achieve that loss to be 0 might not be, right? But at least like I would like to have that loss close to 0.
Okay. Got it. Thank you for clarifying. Thank you so much.
So are there further questions?
Professor,
Yes, please go ahead.
Professor, actually, for tabular data, we are using, the MLPs are for tabular data. In which cases do we use, ML algorithms like XGBoost versus the deep learning algorithm like MLP?
So for tabular data, all the traditional ML methods should work as well as these MLPs,
Okay.
right? So, yeah. Now, what we will see is like, although I'm promoting it as ML for tabular data, what we will see is like for image data, we would modify this basic notion of linear combination plus bias and non-linearity to something else. So
Okay.
that basic philosophy carries out throughout image for time series data, etc. But then what we will see is that the tabular data need not be actually tabular data, but it can be any features that are extracted through some other model. Okay, so that is point number one that I would like to make. Point number two is in ML in general, right? So traditional or deep learning, there is no one size fits all solution. So given now that, okay, so far you had seen XGBoost and everything.
Yeah.
Today you're seeing MLP. Tomorrow you will see something else. Now, the best way to answer which one is good for your task at hand is to run that on all the 4 or 5 models that are possible.
Okay.
And then pick the one that suits your task the most. Now, the model that is good for your task might not be good for something else.
Yeah.
So there is no one optimal solution. There's no one neural network that fits or answers everything.
Yeah.
Okay, so even for you, you might have like 3 different tasks. For one, XGBoost might be better. For the other one, MLP might be better.
If the dimensions are very high, then we prefer MLP and or something like that. Let's say there are thousands of features or so.
So MLP is like a generic black box.
Yeah.
Right. So it need not be fine-tuned for a particular feature size.
Okay.
Okay, and again, there is no hard and fast rule that I should use MLP whenever there is large data. There is nothing like that. So you could basically, again, like the answer is like I would try it on all the 4 or 5 models that I know.
Okay.
And then pick the one that is best in terms of the trade-off between inference time, the memory requirement, and the performance.
And we can completely eliminate feature engineering with MLP.
Yes. Yeah.
Okay.
So in today, we are again like we are setting up this construction of MLP. You don't see how we are eliminating the feature engineering. In the next lecture, you will see that okay, that is not really needed. But having said that, if somebody has done feature engineering for you, it is good to always include that as well.
Okay. Thank you.
Okay.
Professor, one last question. Can you
Yes,
have
go ahead.
functions across different layers in a DNN? Different activation functions?
Yeah. So in principle, you could use different activation functions for different layers. But I was mentioning this a few minutes back that it is often easier to use the same activation function for all the neurons in each layer, and to an extent use the same activation function for all the hidden layers. So that is computationally easier solution. Although in principle and in theory, you could use different activation functions per neuron per hidden layer. It's just the computational ease that it is a same activation function. The output activation function, we will see in the next lecture that it depends on the task at hand. It is not simply an arbitrary choice. It is based on the task at hand.
So beyond being theoretically possible, there is no practical application of having the different functions across different layers.
So now the question is like, okay, so theoretically, somehow like, okay, I can code to make sure that every neuron is having a different activation function and every layer has a different activation function. Now, the natural question to ask is, what is the gain that I get by doing so? Now, what different experiments over the time on various tasks have shown is that choosing different activation functions per neuron per layer will not significantly give you different results and improved performance. So very well, let's use the same activation function, right? That is the common understanding that has emerged over years.
Okay, thanks.
Okay. So Sridhar, I suppose ensemble methods allow explainability better than DNS. Yeah, so one could basically use an ensemble of different, right, XGBoost and DNN, etc. But that doesn't necessarily mean you're able to explain one model better than the other. You might get a performance boost, but explainability needs to we will see later on, particularly for the imaging application, that there is some interpretation of what is going on with these intermediate layers and so on. But ensemble doesn't necessarily mean better explainability, but it could indeed mean better empirical performance.
Yeah, bro.
Okay. So if there are no further questions, let's end this meeting now. We will continue the discussion on these MLPs, particularly tuned for the training of regression and classification tasks, and also some of the final details in the next lecture. So till then, take care, and I'll see you next week. Thank you.